thank you all the organizers for putting together these lectures on different topics on quantum gravity and for our invitation to present this topic, which is known as celestial holography. So there are going to be 3 lectures. And of course, I have selected some aspects of celestial holography. It's not meant to cover everything about celestial holography. This has been a very rich field, many development in the last year. So I have made a selection of what I believe are the salient feature about this program. And yeah, before I start, I want to tell everyone, encourage everyone here to interrupt, ask questions, stop me at any point. I'm not planning to talk, as I said, to Eva for 1.5 hours alone. So please help me in making this lecture a little bit interactive as much as possible. Okay, so let's start. Let me try to motivate a little bit what is this topic about and why it might be an interesting question. So to me, the reason why I got into this field is because of these objects. So this is the black hole in the center of our, well, not this one is in the center of the M87 galaxy, but we have analogous picture for the black hole in the center of our own galaxy. And as you know, black holes in theoretical physics raise the most challenging questions and puzzles that we have, and they're really compelling us essentially to go beyond the laws of nature as we know them and understand what are quantum properties of black holes and gravity. And I think it's fair to say that much of our understanding of quantum properties of black holes has to do with the spectacular advances of what is called the holographic correspondence, which, as you might know, is explicitly saying that quantum gravity, the idea is that quantum gravity can be encoded in a different theory, which does not involve gravity, that lives in a lower dimensional spacetime. And in this regard, one can consider that the first hint for the fact that gravity is holographic in nature is the Bekenstein-Hawking formula for the entropy of black hole here, which says that the entropy of a black hole scales with the area and rather with the volume. And this is very universal formula for all sorts of black holes in different kind of spacetimes. And in retrospect, we can see this as one of the first signature of holography. So the groundbreaking realization of this idea, this holographic principle, has been achieved for anti-de Sitter spacetimes, which, as you might know, have negative cosmological constant. And this is the so-called famous ADS CFT correspondence, where quantum gravity in ADS has been conjectured to be equivalent to a conformal field theory that lives at the boundary of spacetime. So in this picture, we have the idea is that the quantum gravity in this disk, representing gravity in ADS, can be encoded into a lower dimensional field theory here, living on this circle here. So that's been very powerful. However, so far, this correspondence is really well understood and well developed for an ADS. And we know that we don't live in ADS spacetime. So one of the outstanding challenges now in high energy physics is to understand in a precise way to which extent the holographic principle is a fundamental feature of gravity, and whether we can formulate a precise notion of this dictionary between these two theories for realistic spacetimes. So realistic spacetime include, of course, the case of positive cosmological constant, which is the universe we live in, and then you might attempt to understand de Sitter holography. Or another set of realistic scenario is the case I'm going to focus on in this lecture, is the case of asymptotically flat spacetime. So 0 cosmological constant. So why is this realistic? Where this approximation, let's take lambda to 0. We know that we live in a positive lambda, but very small. If we assume it to be 0, it's a very good approximation to describe physics, from collider physics to astrophysics, as long as you stay below the cosmological scale. Then after, you have to take into account cosmological, the fact that lambda is positive, but below this scale, this is an excellent approximation for physics, and in particular, to describe black holes. So the question I want to address with you in this lecture is there a holographic description for quantum gravity in asymptotically flat spacetimes? And if yes, how can we formulate this, and how far can we go? Okay, is there any question at this stage about the motivation or the setup?
All clear, thank you.
Thanks. Okay, so celestial holography is a particular point of view on this idea of developing flat space holography. This is not the only possible one. I think Daniel Gourmiller has given lectures on Corellian holography, which is somehow closely related to this, but still has some different aspects. But yeah, let's dive into the so-called celestial holography program. So if you're interested in this topic, I'm going to list a bunch of reviews and lecture notes on the topic. Throughout these lectures, I am not going to put references for the statements I'm going to give, because it's a lecture, so I don't want to clutter the slides with a lot of names. So if you're interested in the details of some aspects or solution to some exercise that I'm going to suggest, I encourage you to look at the following reference that I'm listing here. So the first reference brings us back to 2018 already, where you will, if you look for the word celestial holography, you won't find it in this book. By the way, it's on arXiv, you can access it freely. However, it was in fact the very building blocks of what will be later known as celestial holography. As you're going to see later, it revealed new connection between the asymptotic structure of flat space and an universal feature of quantum gravity and scattering processes. So it was really the starting point of this program. So I encourage you to have a look at this. And then on celestial holography per se, of course, I'm biased, so I am going to give the physics report I have written on this topic, from where most of the things I'm going to tell are based on. But there are other nice sets of lectures by other authors, which also contain complementary materials to what I'm going to say. And essentially, if you look at this, you can find references therein, okay, for what I'm going to say. Okay, so that's the plan of the lectures. Let's see how it goes. I'm going to first review some very basic features about the conformal structure of flat space, because I want to define a little bit what is the celestial sphere, what is the conformal boundary of flat space. Before even talking about celestial holography, we have to know what is the celestial sphere. Then I will spend most of the time on this section here on celestial amplitudes. I will have to define this basis of conformal primary wave functions. This will in turn define for us what are celestial amplitude or celestial correlators. And I will try to illustrate some of the features of celestial CFT by this example of a 2-to-2 scattering amplitude. And I will also discuss the story about the operator product expansion in CFT, in celestial CFT, with the idea that I was also explicitly asked to talk about, my end goal is to talk about W infinity symmetries, which is the most recent development, so to say, in the field. So this is why I need to talk about the celestial OPE, and I also have to introduce you to this notion, important notion of current algebra in celestial CFT, which will be closely related to what some aspects of Daniel's lecture related to the asymptotic symmetries of flat space, the so-called supertranslations, BMS supertranslations, and superrotations that I think he talked about, even though not focusing so much on the four-dimensional case, which I'm going to. So that's the plan. It might evolve. Let's see how it goes. So let's start with the conformal structure of flat space. So I'm going to start very basic. For some of you, it will be very trivial what I'm going to say. For some of you, maybe less, depend on your training. So let's start with flat space. So I'm going to work all the time in 4 dimensions, okay? I'm going to write down this line element for Minkowski space, okay? This is the unit round sphere metric in theta and phi coordinates. Now, throughout this lecture, I'm going to use slightly, maybe less familiar coordinate system for flat space. I'm going to first introduce this retarded time, t minus r, which I'm going to call u. And instead of working with the theta and phi coordinates for the angles, I'm going to use these complex coordinates, z and z bar, which are stereographic coordinates. Okay, so they are related to the theta and phi angles like that. And if you rewrite the unit sphere metric in these coordinates, you end up with this line element, okay? It's just a change of coordinates. So these will be the coordinates on the celestial sphere. Later on, I'm going to define more carefully. But then you should notice that Z and Z bar cover a sphere. Well, these Z and Z bar are not global coordinates on the sphere. They do not cover the north pole, Z equal infinity. So they are, if you want, a certain patch on the sphere. Of course, you obtain the Riemann sphere by adding a point at infinity. Okay, with taking this complex coordinates. So this is important in light of making globally well-defined statements. So we will be working with these Z and Z bar coordinates for a reason that would be transparent in the rest of the lectures. So with these coordinates, you can rewrite Minkowski space like this. So you see the fact that you have a null time, now you have a minus du square minus 2 du dr, and then you have the round sphere metric, which can be written in this way. Okay? So now we are going to talk about infinity. Holography is telling you that we are going to define a dual theory living at the boundary of space-time. What is the boundary of space-time? What boundary is at infinity? How do we discuss this notion of infinity in a mathematically rigorous way? Well, to do so, Penrose worked out a beautiful construction long ago, which is sometimes referred to as the conformal compactification. The idea of this is really to bring infinity to a finite boundary via a conformal rescaling of the metric. And this is going to allow us to draw infinity in a sheet of paper. We are saying just it's very far away. We're going to be able to draw the boundary of flat space in a diagram called a Penrose diagram. So the idea is the following. So you're going to work with what is called the conformally rescale metric, ds tilde. So as you see, this is just a conformal rescaling of your physical metric here in Minkowski space. And you have this conformal factor here, sometimes called the boundary defining function, omega. And to have a meaningful and smooth, how to attach this boundary in a smooth way, this function omega has to satisfy the following property. So it's the boundary defining function. Namely, it's equal to 0 at conformal infinity, which is denoted by this script I called scry. And if you wish, in order that your boundary has a null normal which is well defined, you need the gradient to be non-zero as cry. If it's not the case, then you're going to be a very degenerate degenerate boundary. It's not interesting. So with these properties, you define your, sometimes people call this ds tilde the unphysical metric, okay? It's conformally rescale metric. And the key feature of this metric is because you have done a conformal rescaling, it will share, so your rescale metric will share the same conformal properties as the physical metric you started from. However, notice that the distance of this in this conformally rescale spacetime will be modified, right? It won't be preserved. However, all the angles and the causal structure, in particular the null cones of your spacetime, will remain preserved because it's a conformal rescaling. And moreover, this ds tilde is regular at the conformal boundary. So it will allow us to define, to really attach to our physical spacetime a boundary in a smooth way. There are many details underlying this construction. Okay, is there any question about that? Now next we are going to do that for flat spacetime. Okay. So let's do that for flat spacetime. So this is an exercise. Here I'm going to give you, in fact, the conformal rescaling that you can do to produce a conformal compactification of flat spacetime. So here is the conformal factor, and you see it involves these new coordinates, big T and big R, which are related to the original little t and little r coordinate, like this. Okay, so what you can show is that your Minkowski's metric is conformally equivalent with this conformal factor with this metric ds tilde square. Okay, so what's the advantage now? Well, the advantage now is that your unphysical metric here is perfectly regular at the boundary, which I'm going to show next. And more importantly, you can see that now your coordinates big T in R have a finite, lie in a compact, are compact, right? They run not from 0 to infinity, they run from -pi to pi, while the sum and then difference and R is positive. So in other words, we can now draw a diagram for this metric, where t plus r and t minus r go from -pi to pi. So this drawing this triangle, this boundary of this triangle here. And what I also encourage you to show, to get familiar with this Penrose diagram, is to convince yourself that if you draw constant t and constant r, little t and little r, it will be this curve in this diagram. Okay. And constant u will be this 45-degree line here. Yep. Question.
Laura, I think in your uppercase T and R, the definitions, do you mean P plus Q or something else? I don't see any other P plus Qs there.
In the definition here?
Yes, that's correct. Yeah. So do you mean U,
yeah.
U plus R, or is that right?
Big T is P plus Q with P and Q related.
There you go. Yeah. Sorry. Yes, you're right. Okay. Sorry. My bad.
Yeah.
Yes, thank you.
There are two change of coordinates if you wish. You could write it in a single step, but it's just more cumbersome. You could write perfect. Big T and big R instead of little.
You're good. You're good. Thank you.
Okay. So again, the upshot is this. Why are you doing this? Well, now I'm doing this because now I have some metric, ds tilde, which is conformally equivalent as Minkowski space. But now the coordinates have a finite range, okay? So again, this conformally rescale metric has the same conformal properties of Minkowski and is regular at the boundary here. So these two boundaries are this oblique line here. This boundary here is called future null infinity, scribe plus, And you have this other line here, which is called pass null infinities cry minus. Okay, there are other points, special point here in this diagram. I'm going to comment on that later. But as you can see, what this conformal compactification here I'm presenting is well adapted to describe massless particle or null rays or everything that is massless, because it resolves very well null hypersurface here. So these are null hypersurfaces. Okay. So let me comment on some aspect of this. So as you can see, when you draw this diagram, this Penrose-Carter diagram, here it's a 2D picture, but you really have to think that each point here in this diagram is a sphere of radius sin r. You can see it here. This is the radius of the sphere. So each point is really a sphere or radius sin of r. And as I said, okay, light rays always propagate along 45 degrees line in this diagram. Now there is another picture that you might see in the literature or in talks, is this shape, is a diamond shape. So these are the same, it's also a conformal structure of flat space. The only difference is that if you wish, now you have unrolled your triangle and you have two copies here with this axis of symmetry of big T here on the vertical axis. And in this diagram, what you really have to think of each point being a hemisphere, and one part of and you have one hemisphere on the left part and one hemisphere on the right part, and together they reconstruct the full 2D sphere. Okay, but these are two equivalent way of doing of presenting the Penrose diagram, but I want to show these two because they both appear in different papers or references. Okay, so this is very classical stuff in GR and conformal geometry. It's very useful and it's very classical stuff to know. And let me just say, in case you're familiar with that in this way of drawing the Penrose diagram, when you identify this point here, so this point should be thought of being identified, you really recover, if you wish, the conformal embedding into what is called the Einstein cylinder. In case you have seen this, this picture is really the statement that Minkowski is conformal to a region of the Einstein static universe or Einstein cylinder. If you don't know what I'm talking about, never mind. But this construction is really important to discuss about the boundary of flat space before even attempting to do any holography. So I focus here on this null boundary. So the future and past null infinity here in blue. This is where massless particle travel to. But on top of that, you have these locations here called the future and past time-like infinities, I plus and I minus. So this is where your massive particles will come from and go to, okay? And on top of that, you have this location called spatial infinity. This is where you reach when you take R very large and T constant. You reach this point. So as you see, as I said here, so each point in this diagram, or each here it would be the same story, is a sphere of radius sin of R. So you can see that at R equal pi, at R equals 0, this sphere shrinks to 0. So these are really reduced to a point, these locations reduced to a point in this conformal compactification. However, is really, I mean, this is really an artifact, if you wish, of the conformal compactification I have performed here, where I especially wanted to discuss the conformal boundary, the null conformal boundary. You can sort of resolve these points by doing another sort of compactification. I'm not going to enter into this fact, but just for you to know, there is a well-defined way of treating in a better way these locations here. If you're interested in what happens for massive particles, or if you're interested in what happens at I0, if you have a Hamiltonian perspective, for instance, you can resolve this point in many different elegant ways. But okay, as you're going to see in this talk, I will especially and almost all the time focus on massless particle, and I will discuss really what happens here at the boundary scri plus and scri minus. I'm not going to talk so much about time-like infinities, okay? But keep that in mind in case you're interested in that. Okay. Is this diagram clear? If not, please let me know. Yeah?
Very clear and beautiful. Thank you.
Okay. So let me contrast this with what happens in ADS. In case you're familiar with ADS, if you're not, this is not going to be very enlightening for you, but if you're familiar with ADS CFT, you see the key feature. So you can do draw this Penrose diagram for different spacetimes. So, and if you do it for ADS, you will see that if you follow Penrose, you will see that the boundary, the conformal boundary now is a time-like hypersurface, okay? And it's very different from what happened in flat space, as I said earlier. And I think that this feature is essentially the reason why trying to make sense of holography for spacetime which are not ADS is so hard. Because here we have a nice notion of time evolution along a Lorentzian boundary. And here we have a null boundary. And as you said, as you saw also with Daniel, null hypersurface are endowed with these crazy math features, which are called Carolean geometries. And this is much harder. This is why it's much harder to define a field theory living on this boundary, on this null boundary. Okay, but let's try anyway. And let's try to attempt to define what is celestial holography. So I have to define for you what is the celestial sphere. So as we have seen, you will have to think about scri, the conformal boundary, has hypersurface which has the topology of R spanned by this retarded time U times a sphere. And this sphere at infinity, which I'm going to call the celestial sphere, is really, you really have to think of it as a conformal sphere that labels null directions at infinity. Another way of defining this sphere, which is exactly what it is the projective null cone. In other words, it's a null cone because it labels all null direction, okay? This is the null cone, and it's projective because you don't care about scale, okay? So you mode out by scale. So this gives you the projective null cone, or CP1 is exactly the same notion. And if you're familiar with the embedding space in the CFT, into the CFT, this is R31, so Minkowski is really the embedding space for the celestial sphere, okay? Just in case you're familiar with this. And let me just contrast this because I often get the question, how many celestial spheres are they? And because sometimes people ask me that because they think, okay, at each cut, so at each constant U cut of scri, I have a two sphere, and that's correct. When you have a constant U cut of scri, it defines for you a two sphere. So they think, oh, okay, so at every value of U here, I have a different sphere. Yes, however, this is not what the celestial sphere is. Again, the celestial sphere is the just labeled null directions, or if you wish, all the sphere at different cuts can be canonically identified, and this identification is equivalent to the celestial sphere. So there is only one celestial sphere at the future, at scri plus, and one celestial sphere at the past. Okay. And later on in the celestial dictionary, we are going to identify these two spheres together. I'm going to come up later on that. This amounts to requiring some matching condition here along a spatial infinity. But I wanted to, if you're not familiar with this notion, there are many nice books on well, I guess the work of Penrose capture that in a very beautiful way. But I wanted to make this point clear because I often see people being confused about that. Yes.
Laura, maybe I don't think it's a question, maybe a comment. There's already a celestial sphere in astronomy, right? So where we describe all the things. So why confuse the terminology? Why not come up with something else? Why this? Mhm.
Oh, because it's really what it is, right? It's really when you look at the night sky, this is really, you're really looking at the celestial sphere. It's really what it is. Well, okay, you are looking at a half hemisphere.
Sure, because of the Earth. Yeah.
Yeah. But if you were floating in space, you would see the entire celestial sphere. So it's really the same concept. It's really the same.
There is a correspondence, yes.
Yeah, absolutely. Very good. Thank you. Okay, so now that we have seen what is the boundary of flat space, what is the celestial sphere. So again, as you see, it's not, it's really the quotient of scry with this r direction, as opposed to looking at the full boundary, which is scry, if you wish. We are going to see how to implement this extra, if you wish, compactification to recast amplitudes into the celestial sphere, as opposed to what Daniel discussed about Carolean manifolds, which are where the boundary is the full null infinity.
So we have a question from the chat.
Yep.
The question is, what is X?
Oh, it's a point in the bulk. It's a point X in the bulk. So yeah, in R3, X is in R3 1. So this span the null cone. Okay. And this is a projective null cone because you just care about the direction of a null ray emitted from a point. Okay, this is what it is. It's the collection of all direction null emitted from a point. Is there any other question or comments?
Thanks. No, so far, no further questions.
Thank you. Okay, so now we have presented this fundamental fact about flat space. Let's turn to the core of the topic, which is celestial amplitudes. So I'm going to tell you already what celestial holography is about. It's about recasting some of the most fundamental observable in flat space, which are scattering amplitudes, and rewrite it in a way so that you can nicely interpret these amplitudes as correlation function of a conformal field theory, a two-dimensional conformal field theory, because again, the idea is that this conformal field theory, so the dual of quantum gravity, is going to live on the celestial sphere. That's the main idea. Now I'm going to explain how you do that in practice exactly. So before doing that, let me introduce basic aspects, very textbook stuff about this matrix and the kinematics of particles. So if you remember, we all know what is a particle, but from a very fundamental point of view, it's a unitary irreducible representation of the Poincare group, which has a definite momentum, p mu. And people have classified this irreducible representation of Poincare. And the upshot of this is that a particle is labeled by a mass, m, and a helicity or spin. Here I'm going to focus again on massless particle only. In other words, the little group represented by the little group, and you have an on-shell condition. So as I said, I'm going to focus on the massless case. So in this case, your momentum is null. And an on-chain massless particle. So you see you have, in principle, you have a momentum has 4 components. You remove one from on-chain-ness, so you remain 3 variables, and you can parameterize any massless momentum, P mu, as the following. It's labeled by an energy. I'm going to denote it omega, and a null vector, Q, which satisfies Q squared equals 0, which depends on Z and Z bar, the point on the celestial sphere. So now again, I'm using this Z bar coordinates. On top of that, of course, you have, if you have a spin 1 or spin 2 particle, you have a polarization vector, polarization tensor. So I'm going to take them as follows. So, and this is, in fact, an exercise that you can do an explicit parameterization of your null vector here, like so. So first, you can check that is indeed a null vector, Q squared 0. And you can form what is called a null tetrad. So it's a basis with Q mu, N mu, which is dz bar Q mu, and these polarization vectors. So what you can check is that it's really form a basis, and you have your polarization vector are normalized as properly, and they are transverse to both Q and N. Okay. So in other words, you can use this Qn epsilon plus and epsilon minus as a basis, and you can use this is often in any celestial CFT or celestial holography paper. You will see 90% change. You see this parameterization for the vector Q mu. It's something very, very useful to do. Okay, so very good. So any massless, the upshot of all this, you can parameterize your massless particle with its energy and such a null vector. And if it's a spin particle, you have also to include these polarization vectors of tensor. So it's nothing fancy so far. How do we usually write scattering amplitudes in any quantum field theory book, where we use the so-called momentum basis? So you have one particle state in this momentum basis, which is labeled by P, or equivalently omega z bar, which is the same information for a massless particle. And you have your creation annihilation operators, which satisfy this canonical commutation relationship. That's very textbook. Another textbook formula is an expansion of a scalar field to satisfy the Klein-Gordon equation. Here I'm going to set m equals 0 later. Well, in fact, it's a bit a mess, but okay. You can expand the scalar field in your momentum in the plane wave basis, e to the I p dot x. Okay, you have a and a dagger. And with using the parameterization I've written before, every time you see the momentum, you can replace it by the by omega, the energy, and this null vector q, which depends on z and z bar. Okay, so this is usual momentum basis story. And then on top, why do we expand in plane wave? Well, because they form what is called a delta function normalizable basis. So your plane waves form a basis. Okay, it's delta function normalizable. So, and this is with respect to what? With respect to the Klein-Gordon inner product. Okay, this is very standard stuff. I'm not going to re-explain quantum field theory. But remind yourself that the physical state are not, strictly speaking, the plane wave, but rather wave packets of plane wave which have finite norm. That's why we are fine with this, because we are always remember that at the end of the day, the physical state have wave packets. Okay. So this is some very basic stuff about amplitudes in the usual basis, the momentum basis. And why do we like this basis? Well, because it's a nice basis, because among other things, it makes translation invariance manifest. So this is the generator of translation. So in the bulk, you have this guy is Poincaré, by the way. This guy is Poincaré. It's a semi-direct sum of Lorentz and translations. And this basis makes the translation invariance manifest because it's just a shift. You see, it's just this phase. And when you act with the translation, this if you want this object diagonalize translation. The whole point of celestial holography is, as we are going to see, is the work in a different basis. It's called a celestial basis. So we are going to write S-matrix elements in what is called sometimes a boost basis or a celestial or conformal basis, has different names. And how are we going to do that? We are going to do this integral transform on. So you start with your one particle state in momentum basis, labeled by omega and this point on the sphere. And what you are going to do to it is you are going to do this integral transform. If you have never seen this integral transform, it's called a Mellin transform. And as you can see, what you are doing here is really an integral over the energy of the particle. Okay, so you are going to trade the energy omega for a new quantity that I'm going to call delta. And I'm going to justify why this is delta, but anticipating, we will see that is the delta, the same delta as the delta as the conformal dimension in a CFT. And the nice feature about this basis is that now the Lorentz invariance is made manifest. And this, in fact, this is nothing, is really tied to the very elementary fact that the Lorentz transformation act on the celestial sphere as the Möbius transformation. I'm going to explain why this has this nice transformation property in a minute. But just the thing I want to emphasize here, we are going to work in a different basis, which emphasizes a different aspect of the Poincaré group, which emphasizes the Lorentz transformation rather than translations, okay? Of course, there are drawbacks in both ways. Here, the Lorentz transformation are obscured, and here the translation invariance is more obscured. This is going to have consequences later on, as when we are going to discuss the properties of celestial CFT. Okay, so let's try to make this a little bit more explicit and work with these and define what are conformal primary wave function. So these are the building blocks of your scattering elements, if you wish, in celestial holography. So instead of working with plane wave eigenstate, on plane waves, so momentum eigenstate. So here I'm denoting plus and minus if it's incoming or outgoing. I'm going to define for you the thing I already advertised before, namely do the Mellin transform of the plane wave packet here. And you're going to have an object which now doesn't no longer depend on the energy omega because you have integrated over omega, but now that depends on this new quantum numbers that I'm going to call what I call delta. You can do this transform. I mean, you can even Mathematica can do this transform, and this is what you get. So I restate X is a point in the bulk. Okay, so X is a point in the bulk, and Z bar our coordinates, our point on the celestial sphere. This is just the gamma function, and what you get is 1 over Q mu X mu to the power delta. So why is it a good thing to do? Why am I interested in using this? Well, for the following reason. This thing that is called a conformal and primary wave function satisfy the following properties. First is satisfy box of phi equals 0. So it's really a wave function. And the reason why it still does is because, well, you can see, so here if you hit with two x derivative, you can easily show that what you're going to end up with is something proportional to q squared. And since q squared is 0, you can see that it automatically solves the wave equation. So these solve the wave equation on the one hand. On the other hand, it transform exactly as a primary, as a conformal primary in a 2D CFT. And it's another exercise to check this property. So if you notice here, so what you are doing here is that you are performing, so you are acting with the Lorentz transformation on Z and Z bar. So you have exactly the analogous transform on Z bar. You put bars everywhere. So it belongs to the Möbius group or SL2C because AD minus BC equal to 1, okay? And then you have the same story for Z bar, and I'm not writing, but Z bar undergoes the same transform with bars everywhere. And if you do that, and on top of that, you do a Lorentz transformation on the bulk coordinate. So this guy transforms as a scalar. This is the scalar conformal primary wave function. But more importantly, it has this Jacobian here, which is exactly the way a primary transform under a conformal transformation, and this delta is called the conformal weight or conformal dimension. Okay, so where does it come from? So to check it, the key feature is the key thing you need to check is that this Q vector that I introduced before, so this guy, what was a null vector, transform like this. You can check explicitly under this transformation. So you can see it has given weights. It has weights minus a half, minus a half. And so when you plug this, well, when you look at how this phi transform, you will see that it will eat this power minor delta over 2 because of this delta here and because of this 1/2 here. Can check this for you. There is another way of writing these weights that people usually use in CFT. Instead of working with this big delta, they split in so-called left and right or holomorphic and anti-holomorphic weights. So in this case, since I'm looking at the case of a scalar, h and h bar are equal to each other. So in other words, I can write delta as 2h or 2h bar or h equal delta over 2. This is the same, okay? But this expression is more generic when you have a spin, because when you have a spinning primary wave functions, then the difference of h and h bar is not 0, and this encapsulates this fact. Okay. Is there any question about here what I'm doing? So far I'm just telling you, do this Mellin transform of plane waves, and you say why do you want to do that? Well, because now you will get a new wave function, but something that transforms manifestly as a primary, a 2D primary of weights h and h bar, and this is exactly what you have in a 2D CFT. So this base seems a good idea if you want to discuss Lorentz or global conformal transformations. And finally, another technical point I'm not going to explain so much is that it's a good basis. Namely, you don't lose anything by doing that. These guys, these primary wave functions, span a complete normalizable basis. When the number, well, this quantity delta, which a priori can be any complex number here, lies on this range. So it's 1 plus I times the real number. And how you show that? Well, it's done in the literature. You have to do Mellin transform of this normalizability equation for plane waves, and show that essentially when the Mellin transform you're doing will not converge unless the value of your delta is equal to this. Okay, so in other words, we have another basis to discuss wave functions, is this conformal basis. Okay, good. So as I said, I also already mentioned a little bit, this is for a scalar wave function. But you have an analogous expression for spinning. So spin 1, spin 2, any spin, conformal primary wave function. The expression for that is similar, even though there are some subtlety related to gauge transformation. So since in this society we like gravity, let me talk about the graviton. So for conformal primary wave function of spin 2 plus 2, here I'm looking at plus helicity. You can build this object, so you just take your scalar wave function and multiply it by your polarization tensor. This is okay. However, it does not transform very nicely as a primary, as I advertised before. So to have a nice transformation law under the conformal group, you need to add a piece here. I'm not going to give the explicit expression here, but basically in practice, what people do anyway is that they just use this scalar wave function. They just use this piece, and you can see that, well, since anyway your amplitude is gauge invariant, it doesn't change the result. Modulo some specific case which have to do with a large gauge transformation that I'm going to talk about in the third lecture. Okay, but the upshot is that this notion of wave function is valid for any spin, and you can build objects that transform as conformal primaries of any spin. So in this case, you have your conformal dimension, which is the sum of h and h bar, and now you have this 2D spin, which is related to your helicity, which is the difference of h and h bar, which in this case for graviton is equal to 2, plus 2 or minus 2, depending on the helicity. Okay, so at the end of the day, for a spinning primary, you have these labels delta and j, which, if you wish, remembers of the energy of the particle, and this one is taking care of the helicity.
Sorry, can I ask something?
Yeah.
So you said that delta is 1 plus an imaginary number. And so my question is if j doesn't need to be an integer with the spin.
So this argument doesn't restrict the value of j. However, well, typically when you work with the with usual particles, then this j is the spin of your it's essentially the spin of the particle that you are scattering. Does that answer your question?
Yes, but no, it's just because I look at the value of delta and I was confused if j could be imaginary. But okay, if it's not, then it's good. Okay, thank you.
No, no, it's not. In this, you see here what is restricted to be 1 plus I. Well, what can be complex in general is this delta. Because why is complex? Well, because I didn't specify anything about delta, right? So when I'm doing this transform, a priori, this delta can be complex because I haven't specified anything. However, you might be worried that whether this integral converges or not. And well, in fact, it does in this case. But for the spin, the celestial dictionary is just identifying this j with your helicity here. There is nothing fancy, no integral, nothing. It's just, okay, you know what? What do you scatter? You scatter a gluon, okay, it has j equal plus or minus 1. So in this sense, the celestial dictionary doesn't do anything on the spin. Okay, so there is no transform.
Okay, thank you.
Thank you. Okay. Good. Thanks a lot for the questions. So now we can turn to celestial amplitude. So now we have everything. So we have done most of the job. I told you how you transform a one particle state. Now you're going to do, so if you have an amplitude, it's supposed to be denoting your usual amplitude in momentum basis, where you have your labels omega, z, z bar for each massless particle. You have a scattering involving n particle. Well, how do you define the celestial amplitude? Well, you do a Mellin transform, as many Mellin transform as you have of external massless particle. So here you do n Mellin transform, okay? And what you arrive at is something that I'm going to write like this. Sorry, there should be different O's here. There is O1, there should be a ... On of delta n. It's not only a one operator. Apologies for this typo. This is better. This is much more better. So by design, because of the thing I said previously, this thing here, so the Mellin transform, n times Mellin transform your momentum amplitude, is going to transform like a 2D CFT correlator on the celestial sphere. Why? Because I show you that for one particle state, it transforms as a conformal primary wave function. So if you do that for all your particles, then you're going to land on something which transforms exactly like a 2D correlation function of a 2D CFT. So we denote this, then we rewrite this right-hand side. We interpret this now as a correlator, a correlation function of a celestial, what we call a celestial CFT, namely a 2D CFT that lives on the celestial sphere. So it's by design, if you wish. There is nothing, no assumption here. It's just the Mellin transform implements the fact that it would transform as a 2D correlation function. And the goal of celestial holography in its bottom-up version, so to say, is the following. We know a lot of scattering amplitudes. Start with your scattering amplitude, your favorite one, say gluon, maximally LST violating, graviton amplitude, anything you want, scalar amplitude, and perform, well, it has to be massless particle for this dictionary, but do this Mellin transform and look at what you get. So you know it would transform as a conformal correlator. And then interpret this as some correlation function of a 2DST and try to see what properties of what kind of CFT is this, if, provided it exists, because as I'm going to show in the next lecture, we are going to see some features of this dual CFT. And the goal is this, just perform this integral transform and derive the properties or give constraint on the dual theory and see how far it goes and what you can say about this theory. So let me say that I have here discussed mostly massless scattering amplitude. But I should be very clear that there is also, you can also do that, namely obtain wave function for massive particles, which transform as a conformal primary. Now, the main difference is that instead of performing this Mellin transform, you will have to do another kind of transform, which has to do with the fact that your massive particle, they don't exit space-time at null, future or null past infinity, but close to here, time like infinity. So you need to derive what is the proper integral transform you need to do. But there is such a thing. I'm not going to show it to you here because it doesn't change so much the discussion. It's just quantitatively a different integral. But you can do massive transformation for massive particle. Okay, so I see we've already reached 1 hour. So maybe it's a good point to ask again if there is any question about any of these aspects.
But there is a question in the chat. One interesting feature of the CPV is the boost is just a Mobius transformation.
Sorry, what is the question? Maybe I can read it.
Yeah, you
Katrina?
can. Yeah, you can take a look.
So I'm not sure. Let me see if I address the question or not. But yeah, this is up. This transformation. This is indeed is a Mobius transformation. So what you can see is that indeed these objects now that you will get are going to diagonalize the boost generator. They are going to be boost eigenstates. Before you had translation eigenstates, now you have boost eigenstates. So indeed, that's the key feature about these primaries. And indeed, this is nothing but a Möbius transformation or SL2C. They have many names in the literature. It's a global conformal transformations. And why this is happening again is from a very geometric point. It's just the fact that the way that the Lorentz transformation acts on the celestial sphere is exactly as a Möbius transformation. So it's just because of that geometric fact. And maybe I hope this answered the question in the chat. If not, just write again. And maybe I skipped that, but now I can give this as some sort of summary. So this is the core of the idea of celestial holography. So you have a scattering amplitudes happening in the bulk of space-time. You can have massless particle coming in, interacting, coming out at scribe plus, or you can have massive particle coming from time-like past and future past infinity that I didn't discuss so much. Instead of working the usual momentum basis with plane waves, you are going to Mellin transform these amplitudes, and this defines for you these conformal primaries of here or operator here, conformal operator in the 2D CFT, which are labeled by a conformal dimension. And then, so you see each of these particles is piercing the sphere at a given point, Z and Z bar. So you really think of this particle piercing the sphere as some insertion of operators on a 2D CFT. Okay, so you can have incoming and or outgoing particles. So you have to take track of these labels. These are these plus or minus. And the idea is to do this transform and interpret this Mellin transform amplitude as a correlator of a 2D conformal field theory and try to infer the properties thereof. Is there any other question or comment about this?
Sorry, can you hear me?
Yeah.
Hello.
Yes.
Thank you a lot. Thanks a lot. So I have a very since some time I have a conceptual problem since you started a bit. So I see in the left hand side you have the Penrose diagram, and I understand that you are checking the scattering amplitude like in the bulk. Okay, and you are relating it with the conformal field theory in the celestial sphere, but where? You see, maybe it's related with your statement that the sphere is always the same, but I'm a bit confused. Can you?
Yeah. So at infinity, at infinity.
So it's scry plus and scry minus, you mean?
Right. So are you okay with the fact that there is one celestial sphere as scry plus? So scry plus is a null hypersurface, right?
Yes.
Which is topologically a line, this is the line I'm drawing, times a two sphere. And that's the celestial sphere. The conformal sphere at infinity is the conformal, is the...
Okay, so the answer to my question is that you're mapping it to the celestial sphere, which is defined at infinity.
Yeah, which is the celestial sphere. Otherwise, I'm not. Maybe yeah. Maybe I was not clear on
No,
the
it's not that.
wording,
It's
but
just because I'm not familiar with this, so I'm trying to understand conceptually.
yeah. So this,
The relation.
what I call the celestial sphere, really the one at infinity. Of course, in any place in the bulk, you have angular coordinates, right? You have a 2D. You know, each point here is also labels the angular.
Yeah, that's why I
part
was a bit confused. Yeah.
of your space-time, right? However, the celestial sphere is the sphere at infinity. Okay. And
I think that.
yeah, this is. I mean, if it's the first time you encounter this notion about, you know, the conformal structure of flat space and conformal infinity.
Okay, I also don't know much about ADS CFT, but I was trying. So I always had this impression that ADS CFT you were relating, like you said in the beginning, like the volume with the area. So the inside with the outside. And here I was a bit puzzled if you're not doing that, but you're still doing that. Yeah.
Yeah, but I'm doing, so let's compare with it. So ADS, what happens is that, so typically in ADS CFT, you have, you have some what you map really, it's ADS with codimension 1 theory, right?
Yes,
You just
yes,
look
yes.
at what happens at the boundary. So if you have a can and the can with the soup inside is ADS, you are mapping it with just the boundary, the boundary of the can of the soup, right? So in this sense, in ADS CFT dictionary, your boundary theory has one less dimension. Okay, so
Yes.
if you have,
That was the idea that I had, yes.
yeah, so if you are in ADS4, your CFT dual is 3-dimensional. Here, notice that it's a bit different because the bulk is 4-dimensional and the boundary theory is 2-dimensional. It's the celestial sphere.
Because you're just mapping it to the celestial sphere, not, for example, okay, so you have the celestial sphere plus time and space, sorry, time and radius. So yeah, you're mapping it to a theory with 2 less dimensions.
Yeah, and what is doing this? Yeah, and it's another perspective as doing what sometimes people call Carolean holography, or what Daniel explained. I don't know if, but never mind. You could also do the following: is say, okay, I have a 4D bulk, and my dual theory lives at this boundary, which is 3-dimensional. But now this boundary is something else. It's a cylinder. You see this, well, sort of higher dimensional cylinder is really scry, so it's 3-dimensional. And that's a different dictionary. That's a different thing to do. It's also a valid approach. You know, no one knows how flat space holography works for the moment.
Yes, we're trying, yes.
We are trying. So the proposal of celestial holography is somehow strange in the point of view of ADF-CFT because you are doing a further dimensional reduction because your celestial sphere has 2 dimensions less as compared to your bulk. So it's really a 4D, I could have emphasized this more, but it's really 4D bulk, 2D boundary duality. And what happens to the other the 3D dimension? It's not that it lost, you see?
Yeah, my question was going to be like, what do you gain? So I don't want to take time from other people, but
no. I prefer to, and I think I'm going to end up the lecture here. I prefer to ask questions.
Okay, so what do you gain in doing this? So in mapping it to less instead of 1, compared with the other approach, I mean.
Right. So what I gain is that I'm obtaining, thanks to this integral transform, something that looks like a correlation function of a 2D CFT. So in other words, in a 2D CFT, you know, why this is appealing? Well, because we know an awful lot about 2D CFT. 2D CFTs are extremely well known. It's also very powerful to have, you know, to have this nice conformal transformation manifest. So if you do the other thing, namely what also I think is an interesting idea, is to work on some theory which lives on this null manifold here. You're not going to be able to recast it as such a nice as a 2D CFT like that, because there you will have the time on top of that. You will have a coordinate u. You see this null time.
I see.
So it's the interpretation as a 2D CFT is not obvious at all. So in other words, again, for everybody, this is key. So sometimes people think, okay, but what happens to time here? Time is lost. What happened to the retarded time here at Scry? It's not lost. It's packaged in a very complicated way. So again, you have your particle. It depends on the momentum, okay, or an energy is the same. The energy upon Fourier transform is the same as your time, okay? The Fourier transform, omega is the Fourier transform of your retarded time. And now, how is this time encoded, or this momentum encoded in celestial holography, is through this delta. So the delta encodes the energy of the particle, But now notice that it's integrating over all energies. So you have a sort of a continuous set of primaries. It's sort of a continuous spectrum, even when you start with a single one particle state. Now you will have a sort of, you see, you have this, you're really sweeping out all of the energies. So this is the price to pay to get something that transforms nicely under conformal transformation. So this is really the gain is explicitly this transformation, this thing. This is the only way to get that. You have to do this Malin transform. The price to pay is that now the way that translation acts on this guy is going to be very murky from a 2D CFT point of view. And in fact, we're going to see that here I have put this, the image of this book, this very classical book on CFT by Di Francesco and others. If a celestial CFT exists, clearly it's not the CFT which is discussed in this textbook. It has very weird features which people are trying to understand. But still, I'm going to argue that still it's still a good thing to do, and you can still gain some insights by doing that. Yeah.
I have a question.
Yeah.
In this regard, you said that this is a weird safety. I think the safety in the safety we are used to, they are flat space time. But here, the sphere is not flat. So maybe there is some peculiarity in concerning this curvature.
No, it's not because of that. I mean, right? You can define your. It's not because of that. We're going to see exactly what I mean by it has weird features. So, for instance, in the usual CFT 2D CFT that we know and love, we have notions of unitarity, locality, analyticity, a set of nice properties that we usually assume. In fact, when we do something like the conformal bootstrap or other things. And what is very hard to you see this sphere is conformally flat. I mean, this is fine. What is more puzzling is exactly which kind of axiomatic properties can we assume for this 2D CFT, and this is what people are actively trying to understand. And clearly, it won't be a vanilla unitary and local CFT like the one, 2D CFT like the one that are discussed and from which we know an awful lot of things. But it's nice. It's maybe a feature that, you know, we should we should study 2D CFT in a more broadly, and that it's an invitation to do so.
Another question. If in the ADCFT we want to do an experiment on the bulk, we do it. We insert some operators on the boundary, and we know exactly what we're doing. But is there the same translation here, the same easiness in doing these experiments and translating them on the boundary, on the celestial sphere? Because I think if we want to do a specific experiment on the bulk, we need to know what we have to do on the boundary to get that.
Sorry, I'm not sure. So you say if I want to, you want to start from which point of view? You want to start from some.
I know that some experiments. I want to do some experiments on the bulk, some scattering experiment.
Mm-hmm.
So I use something on the boundary that would give me this experiment. Translation to the correspondence
Mm-hmm.
will give me this experiments on the bulk in the bulk. But here it seems that it's much difficult to know exactly what is the experiment to do on the celestial sphere that corresponds to what I need to do because of this transformation. It's
yeah, exactly. So so indeed, to
I
do
just
that,
imagine this.
Yeah, so to do that, you would need an exact dictionary about exactly how this duality that I'm arguing for here actually works, and this we don't have yet. So we cannot, for now, we cannot. We don't have, you know, an explicit dictionary from which you see what is the goal of all this is that if we were able to have an intrinsic definition of what a celestial CFT is, a 2D celestial CE is, and from that knowledge, we could reconstruct everything we already know about scattering amplitude in flat space, and also tell us more things that we don't know, such, for instance, some non-perturbative statement in the bulk and so on and so forth. That's the grand goal. I mean, that would, but it's probably extremely ambitious, but we don't have this dictionary right now. So right now, most of the emphasis and works of the community over the last 8 years, so to say, is to go in the left to right direction, namely start with the scattering amplitudes that you like, recast it into this language, and then infer property of this theory. We have not really been able to go the other way around. It's much more ambitious, but first thing to do is trying to understand what are the basic property of this celestial theory. Okay.
Thank you, Laura. So, we have another question in the chat. So I can read it for you, or you can take a
okay,
look.
I can see it.
Or maybe you can then read it out loud, or I can read it out loud so that
maybe you can read it, Eva, so that I think in the meantime.
For the black hole entropy, you also reduce by one dimension. So how can this be a motivation for what you are doing here, where you reduce by 2 dimensions? This is one. And also, just to confirm that I understand, the 2D conformal field theory is Euclidean, and there is no correspondence to time evolution in the bulk.
Yeah, okay, so for the entropy, yeah, that's true. I mean, here I'm just presenting, I mean, again, so we don't have any understanding, of course, of how to reproduce the Bekenstein-Hawking entropy, that would be the ground goal, is that as people have done in string theory, like Vafa-Strominger and others, compute the entropy of a black hole from a purely a CFT computation by means of, say, some Cardy formula or something, and show that you can reproduce this entropy. So this we don't know how to do yet. Again, the motivation here on the codimension 2 holography is rather, again, to emphasize the conformal properties. And let me say also that in ADS-CFT, what I said that it's a codimension 1 theory is not as simple as that, right? Because it's actually, you know, it's the golden example is ADS5 crosses 5, which is equivalent to a 4D CFT. So there is this, you know, this KK reduction. I mean, there are the modes on the S5 are also important. So it's more murky than what I said. Let me know if it does not answer the question. Otherwise, the second part is the 2D CFT is Euclidean. That's true. Yeah. And there is no. Yeah, exactly. So this is what makes this. This 2D CFT picture hard to discuss when it comes to time evolution, because it's not like, as I said in the beginning, as you also probably noticed, in ADS-CFT, the boundary, we have a nice time-like evolution just for along this time-like boundary. Here, this time evolution is encapsulated into this conformal dimension, and the time evolution acts actually shift. How does it act? The time evolution is still there, is still present in celestial holography. Is just its action is the following: is just it shift the conformal dimension, because it's basically how this evolution in retarded time acts. It's going to shift this conformal dimension. So you can see that from a 2D CFT point of view, this is something weird, and there is no analog of that story in a usual CFT. So again, this brings me back to what I said before, is that there is a price to pay for this nice conformal transformation properties, and the price is precisely that, is how time acts. Retarded time acts on this correlation function.
Can you somehow talk about unitarity in time in that setting?
So the way, of course, you know, the S matrix is unitary, and the way bulk unitarity is imprinted into celestial CFT is still poorly understood. I would say it's not understood so well. So this is of course, we know that we have unitarity in the sense of the S matrix in the bulk. However, how this is imprinted into celestial CFT is still an open problem. So as you see, there are many fundamental questions which are not fully addressed. However, yeah, there have been many nice things, new things that you see. The question about these stories: can we learn something that we didn't already know from the beginning? And I'm going to show you that it is the case. So this point of view is useful. As I said, it has drawbacks. However, it has enabled to realize new feature of scattering amplitude that we could not see in the usual formulation. And along the way, it also enriched our point of view about the infrared structure of gravity and gauge theory in many different setups. So it's been a rich story. Sure, you're welcome. Is there any other question?
I don't see
comments
any
or
other
complaints?
question in the chat,
I have one
maybe
more.
from the audience?
Yeah.
From the audience?
I'm wondering about your last slide where you showed this correspondence between this sketching amplitude, where you then apply a lot of Millet transforms, and this is equivalent to some correlation function. Yes. So I'm wondering, I think usually people expect that if I'm working with a CFT, I don't work perturbatively because it's so restricted by its symmetry. But usually if we do quantum field theory, this left-hand side is usually, I mean, we don't really know what this A would be, right? If I think about this, for example, in QED, I can compute this using Feynman diagrams, using a perturbative approach, but I would expect, I don't know, naively, I would think I don't gain much information if I only do this perturbatively about the CFT side.
You say you wouldn't gain. So let's say that you compute, you know how to compute this only perturbatively. What can you gain from there?
Yeah.
Yeah. In fact, it's even worse than that to some extent, because as I'm going to show in the next lecture, you can see that any perturbative computation from the amplitude side, once you Mellin transform, gives you some ill-defined properties about celestial CFT. So there are many hints that maybe it's not a good idea to Mellin transform amplitudes computed in a perturbative way. And then you're going to tell me, okay, then how am I going to, am I supposed to do? Well, there are some way around that. So for instance, there are some limits for in the context of scattering amplitude, which are the so-called iconal limits, which allow to do non-perturbative computations. And in this case, it might be a very useful thing to do, well, to look at in the context of celestial CFT, because indeed there are some pathologies which are inherited on the right-hand side when you only look at perturbative computation from the bulk point of view.
So something like this factorization of amplitudes in the infrared.
Okay, yeah, and also this. So sorry, this is also some aspect I'm going to discuss on the third lecture. Is that yet, even though there are some modulo this aspect I already discussed, there are some universal features about celestial CFT that you can infer, and this has to do indeed with the asymptotic symmetries and this current supertranslation, BMS, superrotation, and so on. And you can infer some very rich organization principle on the 2D celestial sphere, thanks to these universal features which are related to the soft factorization. And so on and so forth. Yes, this is also one of the aspects that personally I've been focusing a lot on, is thanks to these rich symmetries at the boundary of that spacetime, which encode universal features of celestial CFT. Yeah, thank you.
Okay, thanks. I'm also wondering, right now it looks like I could just start with the scalar theory, and from this I would get hypothetical dual theory. Is this what people actually expect, or do we expect to only find the dual theory if we also introduce gravity?
Right. So indeed, so far, what I've discussed today has nothing to do really with gravity in the sense of you could just do this Mellin transform for any field. What gravity brings in the game is something key in the 2D CFT is a stress tensor, the existence of a 2D stress tensor. In other words, the properties of conformal invariance I've been talking about today are global conformal transformation, right? SL2C Möbius. However, what sometimes people want to call a 2D CFT is tied to the existence of a stress tensor. a 2D stress tensor. And as we are going to see, when you have a coupling with gravity, it's going to promote this global SL2C transformation to the full VR0 or the full, if you wish, the local or width algebra. I don't know how you prefer, which name you prefer, but the full local conformal transformations. So you have a stress tensor, and this is what gravity brings more. And this is, I think, what fueled the program is when it was realized that there was a 2D stress tensor, which comes from the bulk, from the graviton, so in a certain way. I'm going trying to explain, and this coupling with gravity induces the presence of a 2D stress tensor for celestial CFT.